It's all good. Okay, so once again, hello and welcome, and good evening. So we are on week 3, and our topic tonight is probability and distributions. Hopefully, all of you are doing okay, keeping well, and preparing well for your first assignment, experimental design, which is basically the foundation stone of your further assignments for capstone, leading to the capstone. So if you get it correct and if you get it in a good foundation, the rest of the journey will be pretty smooth, I guess, and I hope wish you all the best. So our agenda tonight is a mixture of some theoretical discussion and code session. So in previous, so I hope you won't mind if I go a little bit longer, because we will be doing some coding sessions as well as some explanation of the theory. So in the previous cohort, I used to just run through some of the R code examples and no mentioning of explaining of the theory. The other tutor used to do that. So hopefully on mine. That's why I just seek your time beforehand, so we can go in a good pace and can complete the lecture. So I just once again friendly reminder to you, which is your assessment to are due on April 1st. So keep up your good work, and yeah, and look at the rubrics, double check the rubrics so that you comply with all the items. Although your experimental design or study design doesn't have the specific item, but you have to mention that, even that is not applicable or none, or even doesn't apply, you have to explicitly mention that, so that yeah, there is a visibility that you have considered those aspects, although this is not present in your study design. So and about week 3 contents tonight, our topic is basically on probability. So it's basically very fundamental of statistics, and it is basically the core of our statistics, you can say, probability theory. And machine learning's core is statistics. So if you see the idea of probability is the very heart or very core of any data science tools, you can say. So whatever machine learning, whatever approximation, whatever classification, or whatever we do in terms of prediction, that comes from the probabilistic measure. Okay, so that's why we need to know the basic concept of probability and the rules of the probability, and how we can calculate that probability by getting the right sample space. So there comes the combinatorics, which is the permutation and combination of events, or the set we can consider of events. And then another very like a concept of central limit theorem, which is basically the heart of our sample statistics. So no matter what kind of distribution we talk about in the course, whatever, like there are different kind of distributions, we'll see what is a distribution and what kind of distributions are there. So whatever distributions, and we get a sample from the distribution, ultimately that follows a common pattern, which is a central limit that is detected, and that is explained by the central limit theorem. And very interesting theory, you can see that. And then we'll do the sampling, because in this is the whole course is we are doing sampling statistics. So we will know how to draw a sample. We see some R functions to draw the samples, and some concepts about sampling. And then finally, we validate our learning and validate some of the concepts that we get into the theory through some R coding. So this is again like a simple R coding. It's just not we are learning R, as you say, as a programming language, as well as we are learning R using different functions to run different statistical functions, different statistical packages. So it's giving us a both opportunity of learning statistics through R. So let's roll it. So in terms of defining probability, there are 3 aspects, or there are 3 perspective, we can say, to see probability. From a frequency perspective, there's like a frequencist. There is a group who thinks that a probability could be measured by counting the historical observations. It's a kind of you count the number of occurrences happen, percentage of some observations, and you provide an approximate of likelihood of that event happening now or happening in the given observations. So it's a frequency approximation based approach. But more classical approach says if you think like mathematically defined approach, which is a classical approach, it tells that if there is a simple event and each of the simple event has equal chance of occurring, and if you have like n different sample events, like your sample space, if there are n events, then we can define the probability of that particular event happening by some like formula that we are going to learn. So the approach is like, the events, everyone has a probability and has a chance of happening, and then we can calculate the probability from there. So other approach is like a subjective or knowledge-driven approach. For example, the forecasting of a weather, forecasting of a currency market. So that comes pretty much from your knowledge and intuition and pragmatic approach, and from there, from the history, from the observational data, and from your knowledge, we can predict. So ultimately, probability is giving us a kind of a prediction or kind of a like probabilistic number, that chance, basically. What is the chance of happening? That is it's a from 0 to 100% chance. So it gives us a kind of that a figure. So while we are talking about probability, so it definitely is associated with events. So there are two types of event, which is single event or multiple event. Example of single event, so that you can remember, is just think about there are 6 balls in a bag, and there are and the combination of the balls are like 3 red, 2 yellow, and 1. And what is the probability of picking a yellow? So in this case, you have, the event is picking up a yellow, and your sample is you can get any of the balls, from the red ball, from the green, and from the yellow. Everyone has equal chance. So from there, you can calculate a probability of picking a yellow ball. So this is a single event because you are just picking one, dealing with one event. That's correct. So because there are 6, and yeah. Okay, and then multiple event is like 2 events happening together. In that scenario, there are 2 possible cases, like independent events and dependent events. Independent event is that event which the outcome of one event doesn't affect the outcome of other. For example, always learn by example. Like a coin is tossed and a single a 6-sided die is rolled. So there are 2 things, like you have a coin and you have a die to roll, and at the same time you are doing that, but the outcome of the coin, head or tail, is not affecting the outcome of the face of the die. So they are happening together, which is multiple event, but they are not affecting each other's outcome. So this is independent event scenario. But dependent event is a dependent event is a event where the outcome of the first event is affecting or somewhat have an effect of the outcome of the second event. For example, or you can say the first. Okay, I will go there. The concept is called replacement and without replacement. So the first we get the concept of dependent, then I will go there how that can be used to define independent event as well. So even in the case of like you have 52 cards deck in the deck of a card, and you pick one of the cards, okay, and then you don't return the card, then then your card number has reduced from 52 to 51. So next time, the whatever card you want to pick has a less probability than the previous probability, because the number of events, possible events, has decreased. So you are not replacing or returning the card in the deck, but you are pulling the second event or happening the second event without replacing the card. So that means the first event is affecting the outcome or having some effect on the outcome of the second event. because obviously probability has decreased for the second event. So this scenario is dependent event. So independent event is an event where you have replacement. So whatever you do, you replace that so that the outcome of your total sample space is not altered. It remains the same, but dependent event, our sample space has some changes because of the first event. Okay, so some terms so that we can clarify, like, because we are talking about different like a terminology, so we need to be like consistent on that, and we should know the clear concept of that. So probability is not a truth, okay? It's just an estimation, or it's a guide, or it's a prediction. And we usually predict in the scale, like, and it's a visual representation of an event happening or not happening. So you can say it's impossible to happen, likely, unlikely, or there's a 50-50 chance, or there's a certainty of it happening. So we give kind of like a qualifier of an event to happen or not happen. This is basically probability, and we can represent through a probability line like that. An experiment is a repeatable procedure with a set of possible results. So we know there is a set of known outcomes, and the experiment should be able to achieve those outcomes in a repeatable manner. In the case, for example, the case of a rolling of a die, we know there are there are 6 possible outcomes, and we can repeat this a number of times to achieve the same outcomes. An outcome is a possible result from an experiment. So it's a member of your result set. An outcome is a subset, or is a member of your experimental result. Sample space is actually a collection of all the possible outcomes of an experiment, which is basically giving you the set of all events that could happen in an experiment. That has happened in an experiment. For example, in the case of a die, there are 6, like a sample space, there are 6 sample points that consist of a sample space of 6. And each of the item, event, or result, or outcome is a sample point. So an event is basically one or more outcomes of an experiment. Just easy stuff to make the formula to get the concepts of the definitions clear. Now, there are some rules around probability. As you have already typed in, you calculated those problems I mentioned, because that was a probabilistic problem. And since you have reviewed your lecture notes, and you are agile enough to do your maths, so you have done that. That's good. And so to calculate the probability, there are 2 scenarios, 2 setups, as I said, like independent events and dependent events. In the case of independent events, so Venn diagram is a kind of a diagram, which is visualization that can represent our sample space and event in a universal set. So universal set is like all possible happenings. So within that, we have a small, like some events, which consists or makes our sample space. So even our sample space is now consisting of multiple events, different kinds of events. So event A and event B. In the first figure is showing that they are independent because they are not affecting each other's outcome. So this is independent event represented through a Venn diagram. So in that case, the probability of A or B happening is just a simple addition of probability of A and probability of B. But in the case of dependent events, the probability, as you can see, there is a shared space between A and B. So it gives us the probability of A and B. And so that's why if you want to calculate that particular portion of the probability, then we multiply that probability of A into probability of B. But if the probability of A or B in this case is, we have to deduct that probability of A and B. But because since they are independent in the first case, the probability of A and B is 0, because you can see there is no intersection between A and B. That's why the probability of A and B minus 0 doesn't make any sense. So probability of A plus probability of B minus probability A and B will give us the probability of happening A or B in a dependent scenario. Okay. So let's move on. And then the interesting concept, next interesting concept is conditional probability. So this is a concept like if we want to calculate a probability given that something happened already. Okay, so we are conditioning the probability with an event. So an example, look at the example. What is the probability of rolling a dice and its value is less than 4, knowing the fact that the value is an odd number? Okay, so if we know the value is an odd number, so we are now in the process of calculating a conditional probability, and that sample space and the events that are represented through the Venn diagram, as you can see, and you can calculate the probability. So this is an example of conditional probability. You can see that, and how we can calculate, like for our understanding sake, like we can calculate the conditional probability through a probability tree diagram, which I have shown here. So in the first look, let me explain that. So look, if we want to predict like or get a probability of getting the 2 marbles. So in this case, we have 2 blue marbles and 3 the red marbles in a bag or in a pot, and then we want to calculate the probability of getting 2 blue marbles. Yeah, consecutively. Like if you pick one and then we leave that one again, so with replacement, of course, and then we pick the other one. Sorry, not without replacement. So we take the first one and then we don't replace that, and then we take the second one. What is the probability of getting the 2 marbles consecutively? Because that's why it's a dependent scenario, and that's why your conditional probability come in. So in this case, first one, so the probability of getting the blue marble in the first case, you can see there are 2 blue marbles and there are a total of 5, so 2 by 5. And then our sample space becomes like if we take 1 blue marble, then we get a 4. Okay, so we got or we can get like an OR branch. You can say if it is not blue, then definitely it is red, and then we can calculate the probability. You can go the other half of the tree. Now if you go in the top half of the tree, now we are after now we have how many? We have 3 red and 1 blue. And in this case, if the chance of getting a blue marble is 1 by 4, and other is that. So now if we get the n, which is the probability, now we calculate. Say we can see the probability of P of A and probability of P given A. So previously was a blue one. We say get 2 by 5 and 1 by 5, and then we multiply that according to the probability rule, and we get 1 by 10. That's the probability. So knowing this simple formula that we have learned from the previous the probability law of probability or rules of the probability with the dependent events, we now try to get a new formula out of that. So we start with probability A and B now. So because this is the end event, so we get probability of A times probability of B given A, which we got from the top branch of the tree. Now we swap the side and we divide by probability of A. We get a formula which is basically giving us the formula for conditional probability, which means the probability of B given that probability of A is equals to probability of A and B divided by probability of A. So in this case, probability A and B is known and probability of A is known. If these two measures are known, knowing that probability of A is not equals to 0, obviously because there must be a probability of happening event A, then we will be able to calculate the probability of the other event, knowing that probability of A, knowing the probability of A. So this is the formula for conditional probability, and this is how we can derive that from the simple rule of the probability that we have learned before. Okay, so this is the probability chain tree, and we now know the conditional probability formula. Okay, so now the concept is combinatorics, which is basically 2 things: permutation and combination. In your maths, probably you have done that before. The Venn diagram of previous page. Yes, so in the Venn diagram, you can say, knowing that probability of A is odd, that means, you know, probability of A is like if you how many odds you can get, like a 2, 1, 3, and 5, that is the A. okay, and then you have the intersection there, okay, and probability of B is probability then, and we are after how many? We are after the less than 4, so that means the intersection should be 1 and 3, okay, so this is the value. Now we can calculate the probability. Okay, so permutation is the key point is ordering is important. Like is a 1 2 3 is different than 3 1 2. So if in the case if we have to calculate the sample space, so we need the permutation and combination to know the total number of samples, because the definition of probability says like we first need to know what is our sample space, like how many events are there, and then we know what is our favorable event. So the definition of probability is the number of favorable events divided by total number of events, right? So to calculate the total number of events, we may need to calculate either permutation or the combination. So if in the case our order is important, then we calculate the permutation bit of it to get the number of events. If the order is not important, like for example, if there are 5 girls and we have to choose 4 girls out of the 5 girls, irrespective of their ordering, then probably the combination is there, will give us a sample space. But if you say no, A, B, C, D is very important as the order goes, so then we have to get the permutation as because ordering is important in that case. So and the formula, NR and NPR, and in your lecture note you have that. Probably you have done some maths on exercise on that, so I'm not going to talk much on that NCR and NPR. But in R we have a function called choose, which can give us the combination of that combination value of that of the numbers. Now we will talk about distributions. Distributions are basically, in general, what is a distribution? Okay, so I'll give an example. Look at the example of the pie chart. It gives us the breakdown of internet users in Britain in different users. So in this case, the variable is access to the internet, and events are access the internet by mobile or by dial-up or by cable or no internet. And these are the different percentages. So that means from the whole population or from the sampling from the survey, they have found that there are 22% of the people, there are 20 people use the mobile, the internet through mobile, and likewise. And the total is 1. Okay, if you sum up the probability like 0.22, 0.12, 0.47, 0.19, you get 1. So if you try to plot this value in a graph, like we get a value of this, and what does this represent? That represents a random variable and their probability of that event. So in this case, as I said, event is the internet access, and the variable is accessing of the internet. So and then we get that dot points of different probability in a sample space in a graph. So that gives us a distribution scenario. So as a variable could be discrete, as you know, variable could be continuous. So continuous variable can have a continuous value, and discrete value is like you have a discrete value, and then that discrete value from it will have a probability distribution. Okay, so if we do a number of experiments and we try to get these values of different get the values for the random variable, and we try to plot that, and we get a distribution. And if you try to plot that, the plot is the distribution. So given this scenario, there could be different kind of distributions. So we'll be talking about basically binomial distribution and normal distribution, 2 cases. Okay, because these are the most common 2 distributions that there are from a parametric point of view. These are the 2 common distribution, but there are other distributions that we will gradually cover in the next lectures, subsequent lectures. So binomial distribution is a distribution where the facts are there is a number of finite number of trials, and then the trials have 2 outcomes, like either success or failure. Okay, so there cannot be 2 because the name itself is suggesting that binomia, which is bi means 2. There are 2 possibilities of the outcome, either true, false, or success or failure. And the probability of a success is constant for all the trials. So the probability is a constant. If you repeatedly have to go on this, the probability doesn't change. Probability is a constant, and then the trials are independent. The first trial is independent, the second trial, and likewise. So an example could be like a die, rolling of a die, or even tossing of a coin. So that could be like a binomial distribution. Okay, so and if this is the scenario, then we can calculate the probability of getting a favorable event. In this case, for example, if you want that number of k that we are expecting from this distribution, from these experiments, and given that we have an n many of outcomes, then the formula looks like that. So that is already in your lecture sheet, so you know that. So just let's try to do a math. For example, a fair die is thrown 4 times, and we need to calculate the probability of getting 3 2s in a row. Okay, so our k is like 3 in this case, because it is like we are expecting the 3 2s in a row. So what is the probability of getting 2 in this case? Of the dice, like 1/6, because there are 6 possible variations and only 2 can happen once, so 1/6. And then 1/6 to the power k is like the k is 3, and then others is you can explain the 1 minus p is the not happening, the probability, which is not 2, and to the power of n minus k. In this case, total n is 4, because we are having the experiment like 4 times. First, so this n is 4. So this gives us the probability. So this is the one way of calculating straight away if the outcome is like this, like a binomial. But we will prove that in our R session, like we can calculate the same probability from the traditional approach, or the frequency-based approach. Okay, so but that's the handy calculation approach. If our distribution is like a binomial, following the rules of the binomial, we can straight away calculate the probability of a binomial values. And normal distribution is another interesting distribution. It's probably from the continuous variable. It is happening in many practical applications. The k value in the expression 3. Okay, k is the number of favorable outcomes. You can say the number of events we hope to select. So the number k in this case is 3, because we want to 3 2s in a row. We're getting the 2 because it could be like a 4 2, it could be like 3 3. The output should be the same. Okay, so 3 2s. So the possibility of getting 2 is 1/6. That's why k, but k is 3, because we are expecting that 3 should be, we are expecting 3 2s. So k in this case is number of events we hope to select. We hope to get number of that favorable events. Okay, so normal distribution. Yes, you have 3 factorial, 1 factorial there. Yes. Okay, so basically, yeah, if you say n minus k, the nck, that is the formula nck. Yes, n is 4. Then the formula nck is like that. So 4 factorial divided by 3 factorial by 1. So that's the formula. Okay, normal distribution. In many, if you look at like a practical aspect, if you take the samples of the heights of the people, or like blood pressure of the people of a mass, so you can see the distribution comes like a they converse like a bell shape. So this is the general pattern we see, and this is our ideal case for any statistical reasoning, like sample statistics. But the above 3 things I have shown, like in practical cases, probably will not get a normal distribution in many cases. So that different samples can represent different type of distribution, skewed to the right, skewed to the left, or like a uniform distribution. So this is normal from a population perspective. So population, and we'll see that in the next slides. But when we take the sample statistics from a population, that eventually tries to appear as a bell curve, as a normal distribution. So the normal distribution is a distribution which has like a peak like that, which shapes like a bell. Okay, and the peak is basically the middle, which is the mean, and the data is like uniformly distributed across the mean. Like we have a certain standard deviation. So we can explain it better in the next. So the normal distribution looks like this basically. So we have a mean in the middle, and we have the standard deviation with standard deviation unit 1, standard deviation of 2. It likewise is spread across the y-axis like this. And then area under the curve is saying like the different areas, like if we want to get the 66% of the data, then the whole red represent the probability of getting data within this probability range, and likewise. So you know the rule of 66 and then 90 is the 66%. I think, yeah, we have the rules like this, which is like 68%, 98.5%, and 99.7%. So I'll explain that. So these are the different like area under the curve represent the different portion of the data under the probability distribution curve. So this is known because we know the two big parameters from the sample, which is like a mean and a standard deviation. So if these two figures are known, probably then we can draw distribution like this, and we can predict the probability, or we can estimate the probability of some event within this distribution. Because it follows this kind of a rule where it falls. Okay, and we can calculate the area under this curve to get the range of probability within a particular like a particular range within the x-axis. So the case is here another important concept is the standard deviation from the mean is called z-score. So how to get and then z-score, we can transform our values, the original value, to the z-score by these two steps. So we subtract the mean and then divide the standard deviation, and we can, if we plot the same data by transforming this, we get the standardized data. So probably in your like data, if you collect the data, you know, for example, of one of your variables, if you want to like see the distribution of it, probably you may need to standardize your data through this formula. Like you get your data, and then you from the mean and divided by standard deviation, and you plot that value and see the distribution across the different standard deviation from the mean point of from the mean. So this is just an idea of your of your standardizing of variable of your that you want to measure. So let's look at an example. What does the normal distribution can help, and what the distribution can do calculate and does tell us. So if I say 90% of the student at a school are between 1.1 meter and 1.7 meter tall, okay? If this is a statement, so what from this statement, and if we know that distribution is a normal distribution, like the data is coming from a normally distributed data, and from this point we can find that our mean is like a 1.1 point and divided by 2. That adding these two values and divided by 2, we get 4. Since this is 95%, so we know the 95% means there are two standard deviation from across the mean. That means there are 4 standard deviation. The range is 4 standard deviation. Okay, so from 2 standard deviation from the mean left, from the mean right. So total of 4 standard deviation away. So the range of this data is like 4 standard deviation. So now we can calculate the 1 standard deviation is equals to, we can like subtract and then divide by 4. We get this. So that means 0.15 meter. So we can go by 1.15 meter, and then this is the representation of our of our date of our problem statement that we have mentioned there. And this red indicates our sample space. Red indicates our probability of this happening. Okay, so this gives us the probability measure. So in this case, we can say that there are like a linguistic term, likely, very likely, and almost certainty, which is like if you say if it is likely to be within one standard deviation, that means it is meaning that 68 out of 100 should be, which is the first range. Then very likely is the 2 standard deviation, and almost certainly is like a 3 standard deviation. So this, now we got the 1 standard deviation is 0.15, then you can go by this, like if you say 2 standard deviation, 4 standard deviation is like this. Yeah, so this is how we can have like calculate or give an idea if you know the distribution is normal, and we can calculate the probability underneath that curve. So we will see that through our functions. Now we will talk about sampling. As you know, the picture illustrates we have a whole population of data, and we can take n many samples. So take a sample of some numbers. So we can take n many samples, and what can happen, because each sample may have different statistics, but once we get multiple samples, then that becomes some meaningful information to us at the end. Let's see what we can get from that. So sampling variability means like if we get many samples, then sample to sample the information may vary, but at the end we get something interesting, which is identified like indicated as a question mark. So let's try to reveal that. So before we go there is a concept called law of large numbers. So if the idea is, if you repeat the experiment again and again and again for a long number of times, a large number of repetitions, then the value converge to the observation mean. So if you know the population parameter, which is the the population has a parameter like this mu, and our estimate the sample parameter is x bar, which is like taking a sample from the population, and if we keep on drawing the sample again and again, then the sample parameter, the samples mean like average mean will slowly represent the population parameter. That's the law is saying. So in this case, the true mean is 25, but if you say first sample, second sample, and then we got many times the repetition, and ultimately it converging to that, it's trying to represent the population mean. Okay, so, and the sampling distribution is just nothing else. Sampling distribution is you get multiple samples, and you get the data from the samples, and you represent the samples data either through mean or whatever data you want to represent through the sample. You represent that, and representation is the distribution of samples. So it's basically represent the samples you draw from the population. So the distribution of the samples is representation of the same like distribution we have seen, like either binomial or normal, but that is representing the samples, not the whole population. So in this case, the average is this. Yes. So the average of average is basically we are going through the central limit theorem. It will be there. So this is the difference. I think that will clarify most of your doubts. So we have on one hand, we have the population distribution, which is you can see, which is we have an almost equal number of red and blue. In this population, we have the 200 total number of 200, and if you say there are 100 red marble and 100 blue marble, and then our experiment is doing like 20 marbles we want to pick, and we do this experiments a lot of times. Okay, so these are the samples. Like in this case, there are 3 samples are drawn. The first sample is showing like we got 12, because we have to get 20, so we get 12 red, 12 blue and 8 red. And the second experiment we got 8 blue and 12 like nearly like 9 or 11 red, and then we got 13 red. Okay, so we get different variation of red and blue. And yeah, although the probability is 50-50, but never will get like always we get 50-50. Okay, So that's the whole essence of explaining that before. So every time we take a sample, the sample may not be like 100% matching to the probability, because this is the fact and this is our like a prediction. So in this case, there's 50-50 chance, but in practical case, we got like a 40% chance of getting red, and 55% chance we got to get red, and 65% chance we get red. So 3 different probabilities we got. And if we try to continue this experiment like thousands times, and we plot them like this, so this will be our probability distribution. So this is basically, you can say, this is our population distribution, and then ultimately we get our sample distribution, and this is the sampling. And if we plot the probability and the distributions, so we will see this is our distribution look like if a large number experiment. When we will experiment that, we prove that through R. So the same thing, like if you have a population and then we get n many samples, we will, from the previous slides, it will always represent the most of the data will represent across the means. That becomes a normal scenario, like a normal distribution or a bell curve distribution, which is basically the essence of the central limit theorem. So central limit theorem is telling us, like, no matter what kind of like a population we have, what kind of distribution of population parameter we have, if we repeatedly take the samples and again and again and again for a large number of times, for a large number of samples, the average of average of the average of the samples will ultimately converge or represent to the population parameter, which is the population mean. Okay, so that is basically the central limit theorem is telling us. So having said that, this central limit is with the takeaway point from central limit theorem is the means of random samples are less variable than individual observations. So you can see that individual observation is just individual observation and one instance of the event, but the means of random samples are less variable than individual observation, and means of random variables are more normal than individual observations. You can see this, they are more like in the samples, they are trying to get close to the mean of the population. So that is the 2 takeaway point from the central limit theorem. And based on this assumption and based on this like a proof, our like parametric tests, we do all kind of parametric tests in the first part of the statistics, which is basically relying on the central limit theorem because we know the mu, which is the x bar and the sigma, and that slightly represent the population, and that's why we can, with some certainty, with some confidence, we can test hypothesis basically, which is our parametric test. So central limit has another like another example, like another slide to get you more clear. So look, the first figure is giving you the distribution of the population itself. So we have a very haphazard distribution of the population. So the whole distribution, and now from this distribution of whole population, if we take samples multiple times, like samples, we take the number of sample is 2, and we repeat it many times. Okay. The same, then sample number n5, if the number of we increase, and if the number is increased, and then you can see number of 10 samples and the 25 samples we take, gradually it transforms to the normal distribution form. And that means you look, in the first place, the original population was not like a normal, but we repeatedly taking samples from that population, and as the sample size increases, we try to approximate our sample, or try to approximate the population parameter. So now just a little bit of math. So from the central limit theorem, if you think this is so if the question is based on a service records from the past year, the time in hours that a technician requires to complete preventative maintenance of an air conditioner follows the distribution that is strongly like a right skewed as shown in the picture, and whose most likely outcomes are close to 0. Okay, The mean time is 1 from the population is 1 hour, and the standard deviation is sigma. What is the thumb rule for the sample size? Yes, I think that's basically a population of 100. A population of 100 is a small population, so we will experiment that, and you can do the experiment by yourself and see where you converge that, okay, to a normal distribution. So we will share a code snippet to do that. Yes, okay. So does the lecture get immediately uploaded? I think so. There is probably a time lag. Probably I have checked that before. Like it doesn't appears instantly as a video recording. It probably takes time to process behind the scene to like a mess to to some probably just because the chat window is different or like a screen share is different, so it takes away. Okay. So now the math is saying like if we have a population which is showing a parameter, population parameter mu 1 hour and the sigma is 1 hour. And now we also know that your company will service a simple random sample from this population of 70 air conditioners. Okay, so we are taking a random sample of 70 air conditioners given this big population, and we know these parameters mu1 and sigma1, and the budgeted hour is 1.1 hours per unit. Will this be enough to service? The question is like that. So now we know from the mu is 1 and the sigma x, which is like a sample, is like divided square root by n. Then we get the sigma is 0.17. That's basically give us, now we calculate the z score from this. So we get a z score, which is z is 0.83. Where does it like now, since it is a normal distribution, because as we know that from central limit theorem, whatever distribution we get, ultimately the sample will represent a normal distribution. Then from the normal distribution there is a formula. The formula in R, we can easily calculate the probability under this curve. So the probability under this curve is now probability x bar is greater than 1.1. So the budget 1.1, and we get the value like this, basically 1 minus the probability of this, which is 0.2033. If you we'll definitely see more examples in the R coding. So basically this is giving us this area under this curve, the shaded part of that, which is giving us the probability for this particular scenario. That means it is telling us that a 20% chance the technician will not complete the work within the budget time, because it's not probably, yeah, this is telling us that because in the 20 there is a chance of 20%, okay, in the case 20% will be failing the estimation. Okay, now there are some distributions in R, and as we will see some of the examples in the R, which is we have random distribution, which is R by, and the different is like if it's a normal then norm, if it is binomial then binom, and if we get a random number from the distribution we get R norm or we get the R binom. So normal, and we have also another distribution called T distribution. We have not spoken about the T distribution today, but the next slide and next lecture we will talk about T distribution, which is a kind of a non-parametric distribution, because in these two types of distribution we have the population parameter or the sample parameter of the sample statistics at the x bar, mean or sigma is known, which is the parameter statistics. But T distribution we don't have that, so we have to assume something, and then it forms a distribution. So we'll discuss about that non-parametric in the next. So if you need to calculate the probability from the distribution, we have the p norm, we have the p. If you have to calculate the probability from the binomial distribution, then p binom. Okay, and if you have to get the destination, density, we have the d norm and d binom. So let's move on, and I'm going to share my screen for the R exercises. Okay, so let's share my screen. Enter a screen. Okay. Okay, so I think you can see my screen now. So I have prepared some like a notes. Our session, so I will share that with you. And in the previous lecture, I didn't complete a few of the R visualizations in terms of graphs and histograms. So I will cover that at the end of this because we have some histogram plotting that will cover the things that we couldn't cover in the first lecture, which was basic R. So now we try to solve the probabilistic theory that we have just learned. So look by example. So if we flip a fair coin 4 times, and the problem is what is the probability that you will get exactly 2 tails? Okay, so how many, like from the frequency perspective, what are the different combinations we can get for, in the case of like having the coins? So we can get all these combinations like that. Okay, and we can easily calculate that 2 to the power number of times. Like there are 2 outcomes, there are 2 possibilities, that's why it's 2 to the power number of times you experiment, so like as a 4 times. So these 2 to the power 4 give us this number of events, and we are 2 tails. So exactly 2 tails. How many of this all 16s, they have 2 tails, exactly 2 tails. You can see that there are only 6 instances or 6 events which has 2 tails, and that we can calculate with like a because it's not order doesn't matter, so we can use the combinator like a combination function like NCR, which is the choose function, choose of 4 by 2, because we have the 4 and 2 tails, which just give us all the numbers, and in fact these are these kind of numbers. And as we know, probability is like a total number of favorable outcomes or positive outcomes divided by total number of total events. Okay, so and that give us the first definition of the probability, and we calculate this. So we calculate the number of events, and we calculate the number of favorable events, and we divide it to get the probability. So let's see another example. In the example, there are names like A, B, C kept in a pot and drawn in name 3 times returning. Okay, so we pick up one name and we return that. Another one, we return that. Third one, we pick up and return that. Now the question is, what is the probability of picking A all 3 times? So in 3 cases, like you take 3, like there'll be the what is the probability of getting A consecutively? Okay. So in this case, the total events is 3 to the power 3, because there are 3 types, A, B, C, and we are doing it for 3 times. So there could be, these are the total sample space, 3 to the power 3. And we only one case that could have only 3A. Okay, that's why our favorable event is, which is eventually we can calculate, choose 3 by 3, 3 of 3. That means we can, there is only one combination. And the probability we can say calculate like that. Okay, then what is the probability of picking A as the first draw? Okay, so so now all in the first case, if we are doing it 3 times, okay, but now we are getting more relaxed condition. You will get the A as the first one, but no matter the others could be happening, but must be first one should be A. So in this case, total number of the events is same, but our favorable event has increased, because then we have already A in the beginning, but now what are the other possible ways we can get the other event? So 3 to the power 2, because we are experimenting the like A, B 3 times, and we have the 2 choices like B and C. Okay, so B and C come at many 3 to 2 ways. So this is how we get the probability in the second case. Now let's see other example. There are 3 names, but in this case 3 times without returning. So it's kind of a dependent event. Okay, so we are not returning the tag or the lottery or the item, the name we are picking up, we're not returning it back. So in that case, what is our because in the case of deep events, our number of choices is decreasing from the first draw, then further decreasing from the second. So to calculate the total number of events, in this case, we use factorial instead of power before. So the factorial give us the total number. You can easily calculate that if you want to do that by the probability chain, probability tree I have shown. You can do that way, but the rule is that if it's like this, if without returning, then factorial will give you that total number of events. So in this case, our total number of events is factorial of 3, and then which is then we get only one favorable event could happen with all A, and then we get a probability like that. Okay, so this is one way of getting. But how about if we try to get the probability from the independent the rule of probability? Okay, so in this case, the probability of A in the first case is 1 by 3, right? Because we have 3 elements and we have only one A, 1 by 3. But now in the second case, we have only 2 choices, and then we make one choice, and last one we have only one choice. The probability of C is always 1 in the third case. Okay, so these are the 3 because there are 3 cases, and if we run this and if we see then probability of dependent events is probability A, B times C, and we'll get the probability. So let's see if they are same. This one we get it, and same way we get from the formula, we get the probability as the same. So that means we can calculate the same probability in like a traditional approach, and by number of events, favorable events by total number of events, and also by the rules we have just learned. Okay. Now try to see more example. Like there are 8 students in a class, and there are 2 boys and 6 girls. Okay, it makes 8 students. Then if the teacher picks a group of 5 at random, what is the probability that everyone in the group is a girl? Okay, so everyone in the group is a girl. So in this case, we are making a number of choices, because in this case the order doesn't matter. So we definitely go with the combination choice. So in the first case, what is our sample space look like? How many events are there? So there are total 8, and we are choosing 5 over 8. So that means there are these many ways we can choose the 5 people from the 8 8 students. Okay, but now the second condition is of them, how many ways we can pick 5 girls from the 6. Okay, that means that is our favorable events, number of favorable items, because there are 6 girls, and the how many ways we can choose 5 out of 6 girls is this. And now division the rule of the probability, we can get this like a number of all 5 girls, and then divided by total number of choice. That gives us the answer, right answer. Okay, so if you run it, this is the probability. Okay, now we see a binomial scenario. So a coin is tossed 10 times. What is the probability of getting exactly 6 heads? Okay, so we solve the problem in multiple ways. So if you see this, we try to solve the problem as a binomial approach. We try to solve it as like a traditional approach, or even R function. So there are 3 ways we are trying to solve this problem. So first of all, the probability, this is a binomial approach. Okay, so probability of 1, which is like a 10 times. You can see our K is in this case how many? 6, because 6 is heads, and this head by 0.5 is our like a head or tail. 0.5 equal probability. There is the coin is fair. That means there is no bias on the coin. So every head is 0.5 probability, and tail is also having 0.5 probability, equal probability. Remember the fact or conditions of the binomial distribution, the probability over the number of trials doesn't change. So we have the probability given, and according to the formula, we get this NCX times probability power of to the power n, which is the x is in this case is the number of k, n minus k or n minus x. So that means our 10 is the number, and then 6 is our likely outcome, and then 6 minus 10 is 4. So we get probability like this. Okay, then probability 2, we choose 2 to the power 10, which is our another probability. Like we get like, and then probability of 3, These are the traditional definition of probability: total number of events, and then first one is the total number of favorable events. That means there are this many possible ways we can choose 6 heads, exactly 6 heads, and these are divided by total number of events. And then since it's a binomial distribution, and we have seen the formula, we have seen the R function, the D binom is the R function, which can give us the probability of that binomial distribution for 6 heads given the trials, and the probability is 5. So in all these cases, we should get the same result and see if this is the case. So we can see these 3 results. Let me have a quick look on the chat, what's happening. And they're selecting 5. So there are 8 students. How many different ways we can select 5 students? Yes, that's correct. Okay. Yeah, so it's basically, as I said in the lecture, like the combination is giving us without ordering, like without the ordering and preference, like the combination give us the number of ways we can get the result. Like as I showed before, like how many ways we can get the head and tail. If there are 4 types, these give us these combinations. Okay. But in the case, yeah, this 8C5 is telling me the similar, which is how many ways we can get 5 out of the 8 students. Okay, and then second one is telling us how many ways I can get 5 girls given there are 6 girls, because there are 6 girls. These are the possible, and I'm after actually 5 girls all in a row, because the question is what is the probability that everyone in the group is a girl. So that is my favorable event, and these are the count of my favorable events, and these are the total number of events. Okay, so I just explained one scenario for the binomial distribution, which is a coin tossing. Now a slightly difficult scenario, but in this case not exactly 6 heads, but it said at least 4 heads. Okay, that means X is less than is greater than or equals to 4. So that means it could be head could be 4, 5, 6, 7, 8, 9, and 10, because there are 10 times. So we can do the probability like same way, like this. Okay, choose probability of that means it's giving us exactly 4 head, exactly 5 head, exactly 6 head, exactly 7 head, 8 head, 9 head, and 10 head. Okay, because we are running this experiment as 10 times. That means we should get 10 heads maximum. So all the way, so at least 4 heads, like is giving at least 4 to above. So we got 1. So this is giving us 1 probability. But how about if we use a function? Because as I said, because D binom is giving a probability. But if you try to calculate because this is how the integration, if you look, recall your high school integration is what? Integration is just a like area under this curve, right? And integration is basically a summation. So if we try to sum up all the probabilities from this function, then definitely that will become the same function we have written before in the first case. So the D binom function gives us a probability on a particular point, but in this case we are getting probability from 0.4, 5, 6, 7 up until 10 for each of them, and we are summing it up and then giving us the probability. Okay, so this is one way of getting probability. But other way, if we get the probability of less than 10, and if we deduct it, because we know the whole probability is 1, so 1 minus the tail, the whole of the other half of the probability, like if you can recall the binom kind of the curve. So we are getting the area under the curve where probability is 3 to all the way down, like 3 to 1, and then deducting it from the whole probability, that will give us the same probability. So all these 3 things are basically will calculate the same thing, isn't it? So let's see if it's true or false. So the same approach, we can calculate probability in different ways and see. Let's print the result. So we see the same result is obtained, like this is a traditional approach, the functional approach, and then we are summing it by manually. But if you're taking advantage of the functional or the curve and area under the curve, in this case we are taking 3, giving the 3, and then the sample is 10 with probability, and then we are taking the lower tail and then and deducting it. But we can also do the upper tail, but it starts from 3. Okay, so we will get the same result. Okay, so now we'll move on. Like say, like if we say 65% of our people who purchase a sports car are men, and if 10 sports car owners are randomly selected, then the question is find the probability that exactly 7 are men. Okay, so how we can solve the problem, because it seems like a combination, we have to choose. We have some prior knowledge, which is we know the 65% of the people purchase a sports car, so we know that, and it's a main, or it's a kind of binomial problem, right? So we can fit it into binomial equation, and this is how we can do that. Okay, so it is the 7 men, and because we have the 10 sports car owner, and then we got 7 as a favorable outcome. That means 10 minus 7 is a 3, and 1 minus 3, 1 minus the probability given is 65%. So 1 minus p is that the other part of that. So we get that, but we can also just solve the same problem using the d binom on a particular point, which where it's 7, exactly 7, and then 10 is our the sports car, the size, and 6 probability is this, and we can debinom, because since it's a binomial problem, we can fit that and we can run that and we get the result. So, and the same result we get. Now, how many heads will have a probability of this? So we are now trying to reverse back. If we know the probability, for example, in this case, if you know that this is the probability, then what is the total number of because it's a binomial distribution, because we are either true or false, or head or tail, how many heads will have a probability of this? Will come out with a coin is tossed 10 times. So we are now reversing. We know the probability, and now if it's tossed 10 times, then what should be the number? So then we have a function called q, which just give us the number under the probability curve. So we get the probability measure here, and this is the probability, and this is the number of time we toss the coin, and this is the lower tail is equal to false. That means we are calculating the probability of on the other tail, like other portion of the curve. And then if we run that, this means we get 6. That means there are 6 heads. Okay. Now, sample statistics. Okay, sample statistics. So we are trying to get a sample, like I just showed you, like there is a binom function. If it's a binom, we can get a binomial value from the distribution. In this case, if you want to simulate like 1,000 flips of 100 coins. Okay, so this is 1,000 flips of 100 coins, and we get a probability of 0.5. But you can also, if a coin is not fair, if your coin is biased, you can give a different probability. So we get like a sample. This is our sample look like. Okay, and if you want to do a histogram of the sample, you can do that. History will give us a sample histogram. I will present some kind of normal, because we are getting a big sample. Yeah, and like 100 flips. But if we get like a 1,000, instead of 1,000 flips, we get 10 flips from 100 coins. We get, and then we try to put, yeah, you see, it's not very normal. Like, so as I said, that is, we are slightly trying to prove our central limit theorem. So we'll go there. Now find 10 random variables from a sample of 200 with probability 0.35. So again, our binom is the function, and this is the function, which will give us a like a 10 random 10 random values from a sample of 200. Okay, from a sample of 200, and the probability is 3.5, like we did it before. And this is the way we can get a random number from the R binom function. Now let's look at the conditional probability example. Okay, so we have 120 students. We have of the 120 students, we have 50 students taken statistics, 60 students taken algebra, and 20 took both stat and algebra. Okay, so that means we have some commonality between algebra and statistics, which is 20. And if Now the question is, if a randomly chosen student is taken a stat, what is the probability that the student is also taking algebra? Okay, because there are some commonality. So we randomly pick up a student that the student is taking a statistics, but what is the probability that he is also taking, the same student is also taking algebra? So that's the question. So because it's a problem, if you put it in a Venn diagram, probably you can see that there is like a intersection, and now we are in a position to calculate the probability. So let's do that. So the probability of getting a student having a statistics is 50 over 120, because 120 is the total and 50. Algebra is 60 by 120. Then probability of stat and algebra, like we have 20 students taking both, which is 20, and this. Now, probability of algebra given a student is given that and also take a statistics. That is a thing we want to calculate. Okay. So then probability of a stat and algebra divided by probability of a stat. This is the simple, because that's the formula of the conditional probability. And now it since the not mutually exclusive event, because these students are not mutually exclusive, so that means they are dependent events. So we can also calculate, if you want to ask what is the probability of a student having algebra or stat, so we have to add the individual, deduct the common probability. Okay, so that's give us the answer. So our question answer is this, like a probability of algebra given the student also taking a stat is this. So you can run it and you will get the result. So let's move on the distribution side of it. We can see the car data is our available data set in our R package. Empty cars is the data, and we get the car data into our data frame. So car data is like looking like this. We have these the different cars, and we have the car has a mileage, a cylinder, number of cylinder, and we have other horsepower, different values. So we have how many? 32 observations in this data. Okay. Now we try to plot a histogram about the frequency. So this is the histogram of frequency. So in the axis is showing X lab, miles per gallon, and then Y lab is number of cars. So that means this is miles per gallon, and these are the frequency, number of cars in the Y axis. So this is because the total is 32 as numbers. That means the 32, about in this case, our population is distributed into according to frequency of different mileage per gallon. This is the probable. This is our frequency diagram. Okay. Now we want to plot the histogram using the percentage. Okay. So probability equals to true. If we pass the probability equals to true, then it will create a probability density diagram from the frequency diagram. So if we do that, so this is the that means this is our distribution. Okay, probability density is like a sample distribution in terms of probability. So it still is the miles per gallon, and this is the probability of getting like what is the probability? 0.05 is this having 20 miles per gallon. So these are the different probabilities of different cars. And we try to put a line on the density curve. This is our like a lining, like if we try to, this function is calling like we are creating a line over the density function of the taking as the mileage, and this is this line is giving a peak. So you can see this data is not actually normal because we get a peak here and then another local peak. But this is where we can visualize the data. And now we try to put a curve across the mean and standard deviation. Okay, which is because we know this is based on density, because density is coming from the frequency. So where the data is more frequent, there is a peak. But now we are trying to put a curve based on the mean and then a standard deviation. So this is basically our, like you can say, a normal curve. So density curve is giving a different picture, while our like a curve which is based on mean from the sample parameters, which is mean and standard deviation. We try to plot this and we get like that. So our mean is lying here, and our data is distributed across that. And if we try to put a line through that mean, we can draw a line, AB line, and the mean of this value, car data in mile per gallon, is basically our x-axis is mile per gallon. This is our mean. You can see that our total peak is our, like, the bell-shaped like curve is in the middle of this mileage mean. Now, so we have known this data already. Now we have plotted this data, we've sampled the data, and we saw that got the frequency curve. We saw the frequency distribution. From the frequency distribution, we got the probability distribution, and also got the density curve distribution, and also got the the normal distribution, or try to fit them, get the distribution of the curve to get is a normal or abnormal. Okay, it's basically, because to get a normal distribution we need two parameters, as I mentioned. We need a parameter of a mean and the standard deviation, and we plot that normal distribution, a curve, so it looks like a normal. And then now we are ready to apply the p-norm function, because now this data looks like normal, and we can apply different like a p-norm functions to get different probabilities on this data set. So the first question is, what is the probability the mileage is less than or equals to 25? Okay, so the probability we can see, so we can say this is the we can get the p-norm function, and the probabilities mileage is because our probability is plotted across the mile per gallon mpg, so we can pass the 25 as a parameter, and we know the mean and the standard deviation. That will automatically create a normal distribution from this data set, and then 25 will be calculated. Then the probability will calculate it for the value 25. So if we do that, then we will get this result. Okay, so if you see the health function p-norm, okay, so there is a default value. Lower tail is by default true. Okay, so that means I didn't specify lower tail equals to true, but because it's by default, the lower tail is true, because we are calculating the lower tail value, not the upper tail, because it's less than 25, so it's like left tail basically. Okay, so now a bit complex. What is the probability that mile per gallon will fall between 30 to 35? So you are basically calculating a probability of 35. It's just a small fragment of that 30 to 35. So the area from 30 to 35. So we get the higher probability first, 35, and then deduct the 30. And that's the range, that's the small area we'll get as the probability for that. Okay. Like I put another example, you can run it by yourself, but yeah. So now the interesting theory with the central limit theorem. So to do that, as I said, whatever distribution, so we try to get some sample random variables. The R beta function is giving us that like a random variable. So we are getting like a 10,000 random data, and it's basically just run that, and you can see that we get the and that looks like this. So it's right, it's skewed to the right, because I added some parameters which will make the data skewed to the right. That means this is our population. Okay, imagine this is our population, the population of 10,000. Okay, whatever that represent, this is one of the population, and this is the frequency distribution of the different measures of that population. So I got random data and then plotted that. And the summary will give us the summary statistics. So we can say the median, mean is 7.1 and median is 7.3. Now we are trying to prove the central limit theorem, which is if we take repeatedly the samples, that will eventually converge to the population mean, which is mu. So let's run the first case where we are our like a sample size is always taking the sample size of 3, but we run it for this like 10 times. Okay, and we see the histogram for the 10 times. So see this is and then if we histogram of x bar, and if we say summary x bar, which is also getting a sum of average of average. You can see the mean is 7.1, so it still is not looking at like a normal. So we just increase the sample to by 10 fold into 10, probably we'll get a better scenario than the previous one. Yes, getting gradually, and you can see it's a mean is 7.2. Okay, then if we get more sample to run, we'll get more like a closing to the normal distributions, although our population was skewed to the right, but we increase the sample of the sample is 30 still, but we take the samples, random samples again and again. So this n is basically our number of instances we are taking the random samples. Okay, simple random samples. Now if we increase further, even like this, 1000, 10,000, and then it will probably perfectly normal. So like although sample is 30, yeah, it looks like normal. So that means it is converging. Yeah, you can see the mean is already converged to the population. So this is how we can see our sample statistics actually trying to approximate the population the characteristics. Okay, so the now in the static we'll see the p-value that will see how that p-value will interpret, like in which confidence level and which significance level we can say that our sample is representative of the population. Okay, so that's basically whole idea of inferential statistics that we will do later. But the idea is if we take a sample, we try to match, try to infer, try to make an inferences of the estimate of the population parameter through the sample statistics. And this is the core heart of this is the central limit theorem. Now we'll do an interesting exercise because it's just a baby step of our probability based on like an interesting example I have created for you, which is like a food log. So the scenario is you have created your own food log for the 365 days, what you eat in lunch and dinner probably, and then try to predict your like a meal for that day. Okay, so this is the problem. It's a kind of a machine learning problem, but as I said, the heart of machine learning is in statistics. So how that works. So let's see the dataset first. Like this is the dataset food log, and this is loaded in the data frame, which is giving us a date, like a 365 observations. And you have a day like a Saturday, Sunday, Monday, like weekdays, and you have the lunch menu, the main menu, main in the lunch, main in the dinner. Okay, so given these all the observations, we are in a position to predict what we're gonna eat for lunch today, like given the today is a Sunday, or what you're gonna eat in the dinner, given this is like a Tuesday or Wednesday. So this is this is the problem we want to solve. So and also objective is also learn R coding structure through this. So I'm explaining this. So I'm just loading this data set using the read.csv, which is already a data frame type object. Okay, it's the df. So if you see yeah, so class of df, you can see it's a data frame object already because read.csv automatically gets into data frame. Now we are getting these lunch data from the lunch. So that means we are lunch table is giving us all the lunch menu from the data. And then we are trying to get a bar plot. Like these are giving us a kind of a frequency. It's calculating the frequency of the different launch items on that data frame we created. And if we plot that, so you can see the different options. Like you can say fairly distributed across all your up choices. So that means there is no big bias on your different choice of menus. So probably that means yeah, you can see you can increase, like you can see they're fairly distributed like instances. Let me have a quick look in the chat. Sorry to keep you guys long. No, this food log is not part of R. I just created a sample for you, and this is like a new dataset. You will not get the dataset anywhere. This dataset, I have created dataset to give you an example. So it's just a custom-made dataset. So now I want to get the lunch items as unique items. So you can see what are in the lunch items. So if you see lunch items, view, lunch items. Okay, you can see these are the individual lunch items. There are 10 lunch items, and you can see the distribution of those lunch items you have. So likewise, the dinner table, the dinner items, and the frequency of the different dinner items, you created that. Now, this is the preparation of the data from the data set. We have already prepared necessary variables. You can review the code later on. Now, we are creating two functions, basically. Which function? This function, this is also an example of like a learning R. So this function is predicting the probability, not probably, yes, it's calculating the probability of individual item for a week. Okay, so function is probability lunch item and day. The name of the function is probability lunch item and day is a function which takes parameter the weekday, for which day you are and for which main dish. So, and then it is, and within the function space, we are calculating the probability using the traditional approach, the number of lunch events favorable and total number of lunch events. Okay, so in this case, so lunch events equals to the favorable number of events is which is matching our main dish. For example, your main dish is, I've shown one of the example, which is could be like noodles. Okay, so that noodle is basically main dish. So get all the instances you have noodles on that weekday for all that matters. So you get the favorable lunch events, and then you divide it by the total number of lunch events, which is the number of n row is the function to get the number of rows in the data frame, which is in this case 365. So you get a probability. And then likewise, we get the dinner item probability with the same parameters. Okay. Now we have a loop kind of a behavior because you know all the lunch items. What we are trying to do here, we are calculating the probability for all lunch items for a given day. For example, if it's a Tuesday, so calculate the probability of all the lunch item for Tuesday and get all the probability as a list here. Okay, then get the maximum probability, and then finding from the maximum probability and get the what to eat, basically which matches the maximum probability from the list, give you that as a recommendation as a lunch. Same for the dinner. So if you run this, so I just leave the code for you to run it by yourself again. So I just load the data and run it. You can see, yeah. So this is what to eat for lunch or dinner. So probability, yeah, I think this is, I can just run this code. So for the, if it is Wednesday, like, and then probability list, if it for the lunch, what is the probability for the lunch? Sushi. Okay, with the index is 8. That means the probability for Wednesday lunch is sushi across all the menu items, because your all menu items for lunch is like this: noodles, sandwich, blah. So sushi has got the maximum probability that you will have sushi on Wednesday. But there is a flaw in that, because probably we don't consider knowledge, but this is given the number of observations you had from the pattern, and that patterns fall like on the specific week when there's a day, you are most likely to have that. Okay, so it tries to follow this pattern and get from the frequency. But if you consider other aspect, like if it's the weather of the day, like the availability of your of the office or not going to the work, the different scenarios, the different events could affect the result. So this is how machine learning comes into action. You have a lot of variables, a lot of parameters, and a lot of things to model. That's give you ultimately like a kind of good probabilistic measure at the end. In this case, we have only one variable, like the day and observation, but we didn't consider any other variables. But this is how we are getting a like a kind of a machine learning based recommendation of your lunch or dinner item. Okay, so I will share the code, and definitely you take a look into this code, because probably some of the exams in your quiz, you will be given similar questions like this to calculate probability given the different experimental conditions. And yeah, just think which problem is that, and how to get the problem, how to calculate the number of events, and how to calculate the number of favorable events on even it's a binomial distribution or a normal distribution, and then you can use the formula to get the probability. So here is the end of today's lecture, and I'll definitely share the slide with yours. So I just stop sharing, and thanks for your patience hearing, guys. And sorry to keep you late, but there was a big bit of content and I had to cover that. And thanks a lot. Thank you. I'll just stop the recording.